Professor K. J. Baptist. He's a German, come from Germany. Around 1980 something, around that year, he invented this kind of a theory. Now the theory is very simple, very easy to remember. Listen carefully. Any zero above the roof of the building will remain zero. Can you remember that much? So that means this guy is what? S57. You agree? S at row 5, column 7. Right now it is 0, right? What happened to U57? 0. Why? Because Professor Bath, he said any 0 above the roof of the skyline of the building will remain 0. Actually, it is very easy to prove. Can you prove to me why U57 is 0? Why? U57, I say equal to 0. Why? Because U57 is equal to S57, which is 0, right? S57 is right here. This is S57, 0, am I right? And then what else? Subtract the summation of the product and then divide by U55. So now, just think about this summation of product. The summation of this column, this is 57, right? That means you look at what column? Column 5 and column 7. So look, column 5 right here. Column 7 is here. So you see, 0 times 0 is 0. 0 times 0 is 0. 0 times 0, still 0. S45 is non-zero, but times 0, still 0. You see? Is that clear? So the theory is very simple. Any 0 above the skyline will remain 0. Huh? How about this 0? That's a good question. I want to ask you that. Let's see. Let's take a look at this guy. This is S what? S what? S row 6, column 8. S68. Okay? S68. S68. Okay. So here is the story. S68 is 0 for sure, right? So if I ask you, find U68 equal to what? Again, I don't care if it is the actual value, it's not important. I just want to know, is that 0 or non-zero? So what do you say? 0 or non-zero? Non-zero. Let's see. So most of you say this one, right? Okay, let's try to figure it out. According to this formula, U68 should be equal to S68 minus the summation of the product, right? Divide by U66. Okay? Now, of course, this is 0, right? This is 0. So this guy is 0 or not, depending on this term. But the summation of this product will be based on column 6 and column 8. So if you look at column 6 and column 8, this is column 6, this is column 8. You see, 0 times 0, plus 0 times 0, plus something times 0, still 0, plus something times 0. You see? And this is something times something, so non-zero. So that's why non-zero. So now there's something that is important. Listen carefully, any zero above the skyline will guarantee remain zero. Any zero below, it could be either way. It could be zero, it could be non-zero. But the zero above the skyline, it for sure remains zero. Is that clear? Now, whenever you have a zero from the beginning, and then after you do step one, if it becomes non-zero, then we say we have non-zero field in term. Whenever you have a zero value, and after you do step one, it becomes non-zero, then we say we have a non-zero field in term. So, for a non-zero field in term, usually we use a symbol like F, like this. F means field in term. You follow me? So like for example, this guy will become what? F. It will become some non-zero. Agree? Or F. Can somebody tell me, how about this zero? Will it remain zero or will become non-zero? Non-zero, why?
Because we have
this is S79, right? Columns, yeah, because of this product. See, so now you know. So this guy become non-zero field in term F. Okay. Now here's an important secret. If I ask you this question, do you prefer to have a lot of non-zero field in term, or you prefer to have a minimum non-zero field in term? Do you understand my question? This is like F, right? This is F, right? Non-zero, right? This remains zero. This remains zero. Okay? Do you prefer to have a minimum number of non-zero field in term, or you prefer to have a lot of non-zero? Which one do you prefer? Of course, minimum. Because the more non-zero field in term you have to store more memory. So because of that, there was a professor. His name, he comes from India. Right now he's a professor at the University of Minnesota. His name is Professor V.V. Kumar. He and together with his PhD student come up with a special trick that he said, if I give you the system of equation AX equal to B, I give you the matrix A, symmetric pause definite. I give you the vector B, and you want to solve for X. Well, in theory, you can solve it by using step 1, step 2, step 3, like I told you, the Cholesky. But he said, don't do that. You have to do something else first. And let me explain to you what that one is. So, according to Professor see, this is A is given, right? Matrix A is given, and this is given, right? Professor V.V. Kumar, he suggests, try to transform this system, AX equal to B, into the new system. The new system. Instead of A, it will be like A star. A new matrix. Instead of solving for the unknown X, now will be X star will be the unknown. Instead of the unknown B, it will be B star. Now, he said, apply step 1, step 2, step 3 to Lasky. Don't apply in here, but apply in here. But then you will ask me, how do I get this matrix? I know A, how do I get this guy? And then you will ask me, I know B, how do I get this guy? Right? So let me share that secret with you in the next slide. Okay? And for that one, you have to go to page 193 through page 195. Okay, let's take a look at that page. I will show you the secret over there. So, where's that page? 193, 195. Yeah, okay, let's look again. So, yeah, this is a very important secret thing here. Okay? But before we look at this page, let me try to remind you about the sparse storage scheme. Remember last time we discussed about the sparse storage scheme? In order for you to store this matrix in the sparse format, remember we need to have 4 arrays. 2 integer array to tell you what? The location of the non-zero. Remember? Remember? And then the last 2 array to store the actual value. Remember that? Okay. So to store the sparse matrix, we have something like I start row. Like 1, 2, 3, 4, 5. Assuming this is like a last guy. And they have another extra 6. Remember that? And here, what do we have? Of course, I don't remember, okay, but according to the last example, you have like a first location, third location, remember? Fourth location, fifth location. Remember the last time? Okay? Okay. Now, also, I tell you, if you take 3 minus 1 equal to 2, and what does that mean? Row 1 have 2 non-zero, remember? And therefore, you have another integer array, I forgot the name, called J star or something. J star. It will be 1, 2, 3, 4, 5, whatever. So, if you take these 2, subtract, you get 2, right? 2 non-zero, they are in location what? Remember column 4, column 6, remember? According to the last lecture. This is like a column number. Remember that? Right? Okay. So let me go back to this story. Professor V.V. Kumar. It will be related to this story. Okay? Take a look at this system right here. Suppose I give you the matrix K, symmetric, positive, definite. I have the F. And let's say K look like this. Now, those when I put a dot here, it means what? It means 0 value from the beginning. Now, but when I put a F in here, what does that mean? It means in the beginning, those guys have a 0 value in the beginning. But when you compute the U at that location, it becomes non-zero Fueling term. Remember that? Yes or no? Now, of course, you can tell me why this guy become non-zero. Why? Very easy. This is location what? Row 2, column 6. Is that right? This is row 2, column 6. So what is the summation of the product? It will be based on column 2, column 6. Is that right? Is this accurate? What is the location? Row 2, column 6, right? So you take a look at column 6 and column 2. You see? Non-zero, non-zero, that's why it's become Fueling term. So you can see just by your eyes. You don't even have to calculate. You don't need it. You just look at it. And you will know right away, a 0 become non-zero. fill-in term. Non-zero fill-in term. One more question. Number 7. After you calculate u, it becomes what? It will become some other value, non-zero for sure. Do you agree? What is this location? Row 1, column 2, right? So that means S, row 1, column 2 is equal to 7. Everybody agree? So what is U 1, 2? Well, it will be equal to S12, which is 7, minus summation of the product divided by U11. Is that right? Now, because this guy already non-zero from the beginning, so it doesn't matter, this product, 0 or not 0, doesn't matter. This guy, for sure, will become non-zero. But the value may be equal to 7 or may be equal to some other number. Do you agree? Do you understand? So, after you compute U12, the value here in general may not be 7, it may be another number. But at least you know it is non-zero for sure. Agree? Okay. So, if you apply this given matrix, right? And then you apply step 1, step 2, step 3 to Cholesky, of course you will get the solution, no problem. But that will be stupid. Stupid. Do you know why stupid? The reason is because if you do like this, then your laptop computer, how many numbers you have to store? Well, first you count. How many non-zero you have from the beginning? Can you tell me? From this matrix. How many non-zero you have from the very beginning? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. From the beginning, you have 12 non-zero. Do you agree? So, let me tell you this one. 12 non-zero. So, we say NCOEF1 equal to 12. And what it means is we have 12 non-zero value from the beginning. But after you find out the matrix U, the factorized matrix U in step 1, can you tell me how many non-zero do you have? Can anybody? It will be how many? It will be 12 plus a bunch of the F in here. Right? Because remember those F, that means in the beginning they are 0. Remember? But after you find out the factorization U, those 0 become non-zero F, non-zero F. So when you factorize the matrix, you have some extra non-zero. And how many extra do you have non-zero? 1, 2, 3, 4, 5, 6. So you have 12 plus 6 extra non-zero fill-in term. So that's why you have 18. Do you understand? Now, Professor V.V. Kuma, University of Minnesota professor, he said, if I give you the matrix K like this, if I give you vector F, and then you just immediately solve this system using step 1, step 2, step 3, you get the correct answer. You get the correct answer. But it will cost you a lot of computer time. And it will cost you a lot of computer memory, RAM, because you have too many extra non-zero field-in term. Therefore, he came up with a very beautiful secret. He said, okay, this is the matrix given to you, right? This matrix is given. All you have to do is to tell Professor V.V. Kumar the location of the non-zero. Remember I told you, how do you store the sparse matrix? You use two arrays to store the non-zero location. Remember those things? Right? Remember you say like I start row? Remember those things? Those information will tell you the non-zero location. You tell him that information. And then going through Professor V.V. Kumar algorithm. His algorithm will give you the output. And the output look like this. An integer array he called iPerm. 1, 2, 3, 4, 5, 6. Because this is a 6 by 6 system. It will be equal to something like this. This is the output. You understand? You tell him the non-zero location. He doesn't need to know the actual value. He doesn't care. Okay? Just tell him the location. That's all he cares. With that information, go through his algorithm. And his algorithm will provide this output. Now notice, this output will give you the mapping. The mapping between the so-called new numbering system. New numbering system. And the so-called old numbering system. Now, for example, he said, iPerm of 1 is equal to 6. iPerm of 2 equal to 5, for example, something like that. Now, this I just put it in randomly, just to explain. The answer could be, let's say like this, iPerm 1, 2, 3, 4, 5, 6. Instead of like 6, 5, 4, 3, 2, 1, it could be something else, you know, it could be like this, it could be, who knows, maybe like this. Maybe 5, maybe 4, maybe 1, maybe 6, maybe 3, maybe 2. It could be like this. When you tell him the non-zero location, right, he will give you the mapping. The answer could be maybe like this or maybe like that. But here's important. Each of these numbers cannot be repeated. You cannot have like 5 and then 5 again. No. Each number must be appear exactly one time. Do you understand? So like 5, this is 4. Every number in here must appear on the right hand side exactly one time. Do you understand? Now, remember, all of these numbers represent the new system or the old system? The new system. All these ones represent the old system. Now, so that is what his algorithm gives you. The more important question is, what are we going to do with it? How do we use this information? How do we apply this information for our advantage? Remember, I told you, okay, let me explain to you. Remember, I told you, huh? Ax equal to b. Right? The first step is like you want to transform into A star, X star equal to B star. Now I say, from here you apply step 1, step 2, step 3 of the Cholesky. Apply in a new system here. Do not apply the Cholesky in the original system. So the next question you want to ask me is, with this information provided by Professor Vivi Kumar algorithm, right? How do we use this information to figure out this matrix? Agree? And how do you use this information to find out this matrix? Agree? So that's what I will explain to you right now. Very easy. Oh yeah. First, let's take a look. This is a non-zero, number 7. Can you tell me what is the location? What is this location? Row 1, column 2. Now remember, let me write down. The value 7 occur in row 1, column 2 of the old system or the new system? Of the old system. Okay, good, of the old system. Of the old numbering system. So now we want to know, in the new system, this 7, it will move to a different location. This number 7, it will move to a different location in this matrix. Now, row 1 in the old system. Look, old system here, right? Row 1. That means it becomes row what in the new system? Row 6 in the new system. So now you say row 1 now become row 6 in the new system. In the new system. Agree? Now, column 2 in the old system become column what? It be column 2 in the old system become column 5 in the new system. Become column 5 in the new system. So what it means is that value 7 over there, number 7, in this new matrix, it is at row 6, column 5. Do you understand? But remember, because the matrix is symmetrical, so row 6, column 5 is the same thing as row 5, column 6.